A few months ago, at the start of the year, I demoed this, which was a binary adder using trains in OpenTTD Deluxe, which is a freely available and open source game based on a game released in the 90s called Transport Tycoon Deluxe. And basically, this video was just a demonstration of how, using nothing but a bit of track design, you could get a system which would count the number of trains that were passing down the tracks in binary. So you'd have basically a binary adder just requires 3 inputs and needs to output whether there are 0, 1, 2 or 3 inputs in binary. So that will be either 0, 0, 0, 1, 0, 0, 1 or 1, 1. So this system was done very quickly just to kind of prove the point. So if I go along here, what I can do is demonstrate that I can say choose just 2 trains and set them going. So if we choose the one from A and the one from C and then start the train, the 2 trains will run out, and what we will end up will be with 1 train waiting here in the 2's output and nothing in the 1's output. So when I pause this, what will happen is that these trains will set off at the same time. That's very important. They then follow down the tracks and they get out to the other end where they, as you see, this train's now being sent back, and what we have here is 1 train in the output. This train obviously is going to go back to its depot, and there are going to be 0 trains there. So you've got a 1, the correct, the 2 value is 1 and the 1 value is 0, so 2 trains. And again, if I was to repeat this, it will always correctly count the number of trains in the system. That's basically done by the track design, where, because there are a few simple rules in place. There's the trains will have a set of instructions, which is basically to go out to this waypoint here and then head back to their depot, and they will take the shortest available route which is safe to do so. And the way it's determined whether it's safe to do so is by the signals. So the signals will give the trains instructions as to whether the track ahead is clear, and if it goes along and it's got to make a decision between a clear piece of track and an obstructed piece of track, it will take the shortest clear piece of track that's immediately ahead of it. So the way that this works is that this train here, the shortest route this one can ever take is to go all the way around the loop, round and then back all the way to its depot. The only point at which it will make it, that may not be the case if it gets here and encounters a red light here, in which case it will be then diverted onto this track here, which is slightly longer, and then back out. Which is why when these trains were released together, what happened was when the train from B then came through, and its shortest path, if there were no trains, would be to divert onto this rail here. But because there was a train from C would be along here, that would mean that it can't divert onto this rail, so it keeps going on its existing rail. And as a result, it will, and the same thing happens again here, is it could divert down here, but it won't because of the fact that there's a train here, the fact the train's here, so it continues on to here. The thing is, when it gets to here, it's then in this, it then turns this signal here red, because this is here, is all one live piece of track. So when this train hits this signal here, it says this track here is obstructed, so it diverts it onto this rail and sends it back again. And that means that only 1 train is counted. And when you have the system with the 3 trains, is that what happens is that the 3rd train here, all the trains go through as before, this train gets diverted and sent back, but the 3rd train comes in to fill in the one here. So this is basically how the system works, and it was been tested and will count correctly every single time, whether the correct number of trains. So this was kind of just a proof of concept, and it sort of grew a little bit out of hand because I went along and ended up thinking, well, what I can do is I could actually have a system whereby the trains are repeatedly looping around and be recycled, and I can get it to progressively add together bigger and bigger numbers. So I can basically feed in numbers into the system, have it output a much bigger sum, and I don't. Because the trains just go around the cycle, they can be used an infinite number of times. So I then thought, well, how would I go about doing this? So I went along, and if we go into this system down into this part of the map here, you have to forgive this, I'm not going to explain this straight away. So here again we have the same adder. You're going to have to forgive, there's a lot of clutter here which I'll explain, but we have here the same basically adder as before. I've optimized it a bit by shortening the track where possible, but it works on fundamentally the same system where you have your 3 trains going in. You have the units column has a diversion if the 2's column is full at the same time, and the 3rd train will come in to fill it up if there's 3. And again, if there's any combination, they will always divert down to the simplest number of trains as per before. The difference is that now these all loop back round, and instead of going back to depots, they loop back round into their original thing. And there's actually 3 lines of trains in each rail. That's just because of the fact that I can speed up the number of operations happening, is that I can always guarantee there's a train ready to go before without having to wait for the train to, at a certain amount of time, to make sure there is a train, the first train is back again. It just gives me a little bit of redundancy. So this is, and that's that part which you've seen before, and then feeding into here 2 bits of memory. So there's 2 1-byte memory circuits here that basically will stack up these trains into this system. And up at the top here we have a timing loop where a train will loop around here repeatedly and fire the adder to go once every cycle, and that things are set up so it's timed that everything is ready for the next calculation the next time the cycle comes along. And then what happens here is that you have, well, if the 2's column is full, then that's a carryover. That means you need to add in a 3rd bit for the next cycle. So this sends back a signal to this here, which these are relays. These are used all over the system as a way of triggering a green light to go. Because one of the, which I'm going to get into how the signals work in a bit, but basically the problem with the game is I haven't wanted to hack the game, so I want this to work purely on as close to the logic as the original game made from the 1990s. I don't know specifically how many differences have been made from the original TDD to the OpenTTD in terms of how the signal logic works, but certainly I haven't wanted to use any of the special logic that people have made through their own third-party mods. So one of the problems is that there's no way of having a light red and then turn green without having the piece of track blocked. So what these relays do is permanently have a train blocking a signal which will go, and then until that train is given an instruction to then move out the way to release the next train. And that's what you've got here. You have these 2 trains basically constantly looping round in a circuit until a signal is basically stopping one of these trains to divert onto this rail here, and then that goes and releases this train, which then releases this train. It seems a little bit complicated, and I have actually since optimized this. This was my first design. The problem I had is it had to be 100% reliable. Came up with many systems which were a lot faster, but when I tested them on systems where I developed tracks where basically the relays would be fired a high number of times, and I know how many trains the result I'd have to get if it was running 100%, and I was ending up with this quicker system never 100%. But I have since optimized this. But when I did at the time of building this, I was using this 1st generation design. So this system basically will feed in trains into here. This relay here will feed the signal that comes here from the carry, which is where the 2's column goes, sends a signal back to the carry. That then releases a train to be loaded up into there. These 2 rails here are fed from these 2 memory circuits back here, and what happens with the 1, if the 1 goes in, this then sends a signal to the memory, which is stored over here, again in binary. So you have, and the way that this works is that you have a sort of, if the train is in this column, it's a 1, if the train is in this column, it's a 0. And then what happens is these lights will go red if it's 1, or stay green if it's 0. And there's so much to explain here that I'm not going to get into that now. But what I'm going to quickly go and do now is, just for people who aren't familiar with how the signal logic works, is explain. I've done a few demos here. So this here, if we zoom in a bit, this is how the byte works, or the memory storage works. Is, again, as I said, you have 2 rails along here, and as you see, if you've got, unfortunately the colour scheme of the game isn't great for showing this up. I've tried the best colour scheme I can get, which was this purple. But when you have a train in this rail, it's a 1, in this rail it's a 0, and then if you go back here, you then see this expressed here as a binary number. So green is a 0, red is a 1, and as you can see, you've got a 2, an 8, and a 32, which are in red. The others are all green, which adds up to 42, which would be this expression with the trains on that rail and that rail. So that's basically how the system works in terms of storing data. So what I'm going to do is quickly run by how the signal logic works in the game, because, as I said, the important thing to clarify here is that the trains aren't given any special instructions. They're not given any logic at all. They're literally told just to go around in a circuit. Some are given waypoints, some are just told just to go backwards and forwards all around. But then they're never told, oh, if this state happens, do this. They are just following pure route, the shortest possible path that's safe. And the only instructions in this come by where trains happen to be at a certain time, triggering the logic of the signals, which then makes everything happen. So here what we've got is the simplest type of signal. Now in the game you have the signals, and you go along here, the simplest type is here, which is called a block signal. And all this does is, if there is a train, from this signal going forwards, there's a train in a region of track which isn't protected by other signals, it will give a red light. So as you can see, there's a train here, there's some signals here, but there's a train along here, and if it's on this part of the signals, then it means that this is unsafe for trains that are not in there. So this is then giving a red light to this train here, and as you can see, this light here is also red, but that light there is green because it's saying that piece of track ahead is clear. This light here is green because it's saying that piece of track ahead is clear, but again the signal's red. But if I then go and tell this train to move along like this, and I go and get it to move out of the zone there into this part of track, you can now see that all these lights have turned green. It's now safe for this train to go ahead. And yeah, that's basically the most simple type of logic. So if I was to then start running these two trains at the same time, you'd see that what would happen is that this train enters here, sets that to red. Now it's left. It's now gone green again. This train is coming back. This one's entered, so that's made this one red. This train can't enter until this leaves again. So this system will make sure that these trains can enter this bit of track, but only when it's safe to do so. So that's kind of the most simple thing and type of gate that you can use. But the next example I'm going to show you is an example of an entry and exit points. Now what we have here is an entry signal. Here we have two exits. These are just standard block signals which we showed in the last example. So what happens is the exit signals work kind of like the block signals. If the track ahead is clear, they will show it as clear. But what they do is they pass the signal down to an entry signal. If the entry signal has if it has at least one green light from any exit signals that feed into it, it will show a green light and direct the train to the quickest possible green light. If they're all red, it will show a red. So at the moment what you can see here is that this train here is in this piece of track here, so it's showing this as a red, but this one there's no green light, there's no train in here, so it's green, and as a result that's showing this as green. But what will happen is if I start this train here, this train will go backwards and forwards, and these lights will alternate, and there'll be a brief period when the train is in the middle and therefore technically blocking both bits of track, that both of these will be red and that will turn red. So if I start the train, you'll watch this, so it's going forwards all the way back. If you watch that, briefly both are red, that's red, but then it goes there and this one switched to green. So as you watch this, so that's red, and now it's going to switch into the other side, and that's now red. And so then if I start this train going, this will always go towards the green light. So this is going in there. That actually does technically stop this train from entering there because of block signals, but yeah, now it's going to go there, and now every time this comes round, this should, in theory, it will ever go towards the green light. But what can sometimes happen, which is where timing comes very important with these systems to make sure you don't get blockages, is that sometimes when this switches, is that this will be going to a green light, and then that will then turn red at the last minute. So it will always be heading towards a green light unless it receives instructions otherwise. Now that's been very important in the design, but basically that's the importance. The importance of these is that you're sending signals back down the line, and yeah, so that's what we've got going on here. Finally, the last type of signal I need to show you is a variation of that. It's a combo signal which does the job of both type an entry and exit signal. So it both will both send some information back down the line, but also read ahead. So, and the reason that's important is that sometimes you need to check if the track ahead is clear, but also check if there's a red signal up ahead to pass back down. And an example of where you might want that is in here is what I've got two. I want to have this light here, which is a start signal, to be green only if both of these bits of track are clear at the same time. In this example, I've got one. And I know that in this example it's kind of pointless because it's just one train going around the track. But I could, for example, I could have two looping trains, or I could have trains in different areas going through here, and I need to know whether or not this is clear. So what happens is that this train is going to enter in here. If either of those have got a train in there, this will return a red light. These are the combo signals here. They scan ahead to check that this is clear, but they also scan ahead to check that this exit 1 is also clear, because this is a two-way. I mean, it's difficult to see. If I zoom in a bit more, you'll see. But this light will scan if this bit of track is clear. This light will scan if this bit of light is clear. So if that's red, it will turn this one red. But also, if this bit of track is blocked, it will send a red. And then what it does as well is pass that the status of this light will be passed to this start signal here. So just basically you see that in operation. I'm going to close these two windows, get this one open. If I start this train going, there's this bit of track here is cut off from the system. You've got just simple block signals here. If the train enters in here, this becomes a live bit of track with the train in. If it then when it passes over here, this also becomes a live bit of train as a no-go. So if we go in there, you're going to go in there. It's red, and it's turned this one red, it's turned that red, which turns this one red, which then, because both of these are red, but once both of these are green, or one of those, or if one of those were green in theory, then that will stop it from happening. But I need to have it done this way, because if not, this train passing through here will stop itself from entering into the next phase. So, and there are very many, it's difficult to come up with a very simple example as to why this is important, but it's been fundamental in actually getting a lot of the relays and stuff to work in the computer. So if I start this train here, this will be green, this will go along. Green light is great, it can go through. And because of the way the signals are set up, this will never send a signal back. So this train will always be free to run. There's nothing from this train can do to stop it, because of the way these signals are one-way bits of track, because there's no signal in going back the other way. So you see it's red, now it's clear, now it can go through. So what I'm now going to get onto is going to give you a demonstration of the train, of the adder running. So I'm going to get it to go and add together two numbers. So if we go into here, what we can then go and do is I can then go and show you that one of the memory circuits is already loaded up. So if a train is on this rail, it's a 1. If a train is on this rail, it is a 0. Again, 42 has been preloaded into here, so we've got the 2, 8, and 32 loaded up. And what happens is that when these are released, is that these trains here are all scheduled to run between this waypoint here and this waypoint here. I'm going to zoom out a bit. So, but yeah, every single train is this. You've got one set of instructions, which is to go from this waypoint to this waypoint, and it will go around here, and it will always take the shortest path. So what happens is, if this this is where all your combo signals come in, is that here we have this line here feeds the instruction to turn this light green. That then goes, the train will then go forward. This light here will then be based on the colours of these lights here. So this light will be green if this light is green, which is coming from this signal here. And that's the shortest path. So the shortest path for this train to get back to its waypoint is to go and turn left here and go down this rail, which puts it in the zeros. But if it's been told to load in a 1, is that this feeding back from this circuit here is that this will be a red light, which makes that a red light, which means that when it gets to this signal here, is it will be told to go down the longer path, which is round here, and down along this rail, and put it into the 1. So you load into the memory. That's basically where we're loading in. Now this, I have to point out now, this computer isn't finished. I mean, there's I'm going to have to be doing a lot of things manually, which will eventually be done automatically. So what I'm going to do now is to give you a demo of loading in a signal into the computer. So I'm going to, I could use these all here are feeding back to memory readers and stuff like that, which I'm currently building. At the time being, I'm just going to cheat a little bit and control this a bit manually. What I've got here is we've got this train here. If this train is here, it will send a red light to here, which will divert a train onto the 1 rail. So what I'm going to go and do is enter in to here the number 15. So that's quite easy to enter. It means that I just have to have 4 ones followed by 4 zeros. Okay, so to do that, what I am going to do is first of all tell this train here to be writing a 1. So I'm just going to give it an instruction to ignore the signal ahead, and that will just park it straight into here. Now, as you can see, that's now passed down a red light here. This light is still green though because it has a clear path going this way. So now what happens is that when I can now tell this train to ignore its signal ahead. I mean, this again could come from here, but it's quicker for me to do it manually. If I send this train forward, you will now see that it will hit this green light, won't go down that way because it's red, it's now going there into the 1. So I can now do this. And you can see here I've got 7 more trains all lined up to be loaded into the adder. So what I'm going to go and do is slowly take each one of those to slowly ignore its head, and then that will load it along into the next one. I need to wait until it gets to the red light, but yeah, that's basically how this system works. So yeah, okay, and I can now I've moved this train out of the system. That's now paid this light green. So when I go to this train here, the next train along in the system, these will now divert onto the 0 rail. So put that one there, and you see now onto 0 rail. So what we are about to do, or we'll eventually be doing, is adding together the numbers 15 to 42, which, as many of you will probably have worked out, should give us the number 57. What I then need to do, I guess, is to show you how there is this the way the system works. There's a train that will run around here, and every time it goes through certain points, it triggers different parts of the calculator. The first thing it does is it goes through this gate here, and when it enters in here, this then sends a signal to this relay, which sends a signal over to here to run the adder ones. Now, at the moment, there aren't any trains loaded. Now, just because, again, when this system gets set up, it will be instructed to load the first bit into the system. All the cycle does is every time it goes around one is that it goes through here, it just tells it to run whatever is in here. I will go and get that first bit preloaded in for reasons which I'll explain in a bit. This train then runs along this loop, it goes along here, and this is where it sends the instruction to load the next bit into the adder. So this then sends a signal down here, through to a relay here, this relay there, sends a signal to both of these memory circuits to send the next bit over. After that, it goes around a bit longer, over here, loops back round. This is just, the track's laid out, it's all done by timing. So it turned out when I first built it, it wasn't quite long enough. So it loops back here, it then gets an instruction here, it runs through this gate here, which tells the memory circuit to write the result, whatever it's received, whether it's a 0 or 1, into the memory. It then goes back through here, loops through here, and it does it 8 times. So if we go into here, the train, we can see the train is here, and I've given it a set of orders. And if we look down there, it's got 17 orders, because what it does is it goes round is you've got 2 points on there. There's these 2 points here, so it's told to go between these 2 points and loop round, and then after it's done that 8 times, it's then told to go here to cycle start here, because there's going to be an instruction later on which when the adder is told to go, it fires that and then it goes. What I will do is, because at the moment it's not presently adding in the first bit, is I'm just going to go and cheat a bit, and we'll trigger that to happen. So this is done by this relay. So if I just trigger this train here to bypass here, what you will see is that it's released both of these 2 trains here. One's a 0, one's a 1. This one's a 1. So this one's then sent along a signal here. This then diverts, through loads of things, causes this train to go through. This one hasn't received that instruction. So what we then have is that input B, which is this input here, is given it a 1 to load in. Input A has given it a 0, so that's told it to not load any train. Okay. So what I can now do is set off, actually no, I won't set it off just yet, but yeah, that's the first bit loaded in. What we're just going to quickly do is explain the memory. What happens when it outputs is that, as I explained before, if it gives 2 trains, at least if it's got a train in the 2 columns, that sends a carry there which will load in the 3rd train and then add together 3 trains. If there's a 1, then that means that it has to write a 1 to the memory. So that then sends a signal all the way down this rail here into here. This is again another of these relays which you see. That then moves this train here into here, which means that when this relay here gets a signal from the cycle, is that then if there's a train there, it will instruct this to write it as a 1. If there isn't a train there, if the train's still parked there, it will write in a 0. And this is a smaller version of the input memory circuits that I was loading up earlier. This should, in theory, when I click go on this, now add together 42 and 15. So I'm setting it to go. So we're going to go along, we're going to follow this train, it's going to go along here. First thing is it's going to cycle start, because that's the first instruction, but it will do the last instruction it was on. It will then loop all the way along over to here. There you go, it's going to fire in here, it's going to then fire a loop there. That's going to send an instruction here. That then will divert this train here, will be diverted along onto this rail here. This is then the relay in action. That then sends this signal here. That then releases both of all three trains here. But there's only one. That means it's going to output one. This then goes along here. This meanwhile will have already set the next trains to be loaded along in the next system. But yeah, going along there, it's got a 1 there. There's all sorts of things going on here. This has been delayed. These are all delays and stuff built in, which I won't explain specifically now. This is now sending along the signal along to the memory. So this is now moving this train will now move along into here. Okay, and now this at some point is going to get an instruction from when this train here enters into the write to memory gate, which is coming up very shortly here. It's about to go through it. She's just going to loop down here. This here, go along here, it's got a write to memory. That then will eventually see this train should divert onto this rail. Yep, okay, that then writes along here. This will now send a signal along to this train here to be written into the ones column. And then this train here is just a delay to move this train back to its reset position. Now if I go along here, we should then be seeing, yep, the next two trains going along, which were again 2 and 2, because again, so now what we should do is get a 0 outputted here, which is correct. We'll get a 1 outputted here, which will now send a signal to the carry, which the carry relay will be triggered in a second. So this now goes along here. This inputs into there. That now sends along a signal to the carry, which will be, that then loads in the 1 here. Now eventually we should also be in a second getting the signal coming in from these trains, which will be inputting the 1 here, because we had in one train we had a 0, and in one everything we had a 1, because it was 1 1 1 0 and plus 42. So yeah, we're going to end up along here with our 2 trains. This is going to now add together. Try to work out if I've actually worked out a sum which is going to have 3 in them. It'll be unfortunate if we don't, but so yeah, now we're going along. This time we've got the one in the carry rail before. As you notice, this is diverting onto that rail, that's diverting onto this rail, again 2 along it, and now it just behaves as if they've been 2 in the first rail. Again, it's going to send a 2 to the carry, and this one's going to go all the way around and back again. So the carry should now be being loaded in. Yeah, that's going along, going along, going along. Carry will now be fired up. We now should have 2 trains. No, should we have 2 trains? So actually, we're going to get our 3 trains going at once. So that was very fortunate. So now we're going along here. This train, the timer 1 is going along. It's going to write the last result to memory, which, if memory serves, was a 0. It will be, yeah, and now the 0 is being written, but now we're going to go and in a second it's going to come back round, start the cycle off, and we're going to get to see 3 trains go at once. I hope you're all ready for that. So there we go, it's going in the gate. It takes, because the current relay, this slow relay design, it sometimes takes a second for these signals to go through, but eventually, yeah, there you go, all 3 trains are now heading off at once, and so what you'll see is, as before, the 2s go along there, that diverts this one onto here, that goes along there, and this goes along into here. In a second, these now get sent off again. This will write a 1 to the memory and a 1 to the carry, and then we're going to get ready for the next. And if we go along here, I mean, these numbers are now kind of meaningless because these trains are advancing along, but but that obviously those numbers only meant what they meant before the sum was begin. So what we've got here is the 16, 32, and the 32, 64, and 128 one left to go, and it's currently writing the value of 32. So that should be going through into the adder. So yeah, and so here we go. It's now coming around to complete. So now it will set off the 32s now as it goes through. Now you'll notice that there are bridges here. The reason there are bridges here is because bridges slow the trains down, and what happens is, in order to get these relays to work, is that I have to guarantee that the train is between two signal gates for a certain period of time. And if I had just unlimited maglev track, that would be a really long bit of track. But by putting this really slow bridge in the way, it just means that the train enters the gate and it's there for a long enough time to make sure that this relay fires. And that's what's slowing the whole thing down, is based on this. I do have a much faster relay design that I've come up with, which is probably at least twice as fast, if not, or it's more response time. It's rather than speed. It's like because what happens is that it enters the gate, but then also it has to then fire another train. So this train is permanently sitting, waiting for one of these trains to be. As soon as a train gets diverted onto this extra rail here, that then means there'll be a period in which this reader thing here is empty, and that then gives a green light. And this system is all designed about keeping this train here unless it's absolutely certain that it's received a signal. And it has to also be that it can't just be absolutely certain it's received a signal. It also has to work that every time it does receive a signal, it fires. So it has to work 100% reliably and not accidentally firing, but also not firing when it should do. And getting that system to work 100% reliably has been the key part in getting this machine to work. Okay, where are we standing on the train? Okay, we've got 2 more trains to go. So unfortunately there isn't much way to speed this up, but I think we are now all on zeros, because so it's now loading in the 64. So it's about to write the 32. Once it writes the 32, if we go there and it isn't showing 57 after it's written this bit here, I'm in trouble. If we go along and have a look at what's happening, okay, it's writing this one. Okay, there we go. So, moment of truth. We have got 1 plus 8 plus 16 plus 32. So, that is 48. That is 56, that is 57. So there we go, my calculator worked. Have obviously done many tests before that and it's worked, but yeah, that's the basic system that I've got in place. But the thing is that, as I alluded to, the system has grown quite a lot beyond this, and basically I came up with the idea of, using this system here that I've got here with store memory here, is that I could use this system as a way of creating sort of almost RAM. And my idea is to have loads of trains stored like this, and then load them in to these systems here through. So I could basically get a system set up where it would choose a RAM set. If you call these RAM chips, I mean, it could choose a RAM chip to read to, choose a RAM chip to write to, and then basically add 2 numbers together. And if I zoom out and then go along here, is that what I ended up doing, and this looks really messy because it is, but what I have here is 8 examples of RAM chips that I set up. So this was this is a very, very fast way of reading data. So basically what I can do is I can store trains in these systems, which are exactly the same as the output memory circuit that you saw on the adder. But what I then do is I can then read the result directly from them using these train lines, because these are using signals. So these here, if we zoom right in here, what we have here is an exit signal reading what is here. That won't pass any more information than is there a train immediately ahead. We have combo signals and stuff set up here. So these are entry signals. So these will only enter if it is clear and if there isn't a red light ahead. These are combo signals. So that means that these trains are constantly will stack up, and it can also create a readable output. So then what I can do is take the readings from these, and all these lines in here are doing is basically getting together the same output. So this is collecting all of the this is the 128s. All the 128s are being lined up later on. All the 64s, all the 32s, and then they're being run through over here 3 sets of switches, which will allow me to select a specific memory chip to read. And the way that these work is by basically blocking off trains into certain sections. So if you can see all on this bank here, these trains are always in the same sector. So that basically means that both through using 3 bits, I can select one of 8 chips. So I can then control these. Again, this isn't the final interface because this will be automated. But if I was here, whichever side of these signals these trains are will depend which side all of these will then control all of these trains. So if I go along to this train here, which is this train here feeds off all of these trains here. So if I go and set this train to move to the other side of the track, okay, it will move to the other side of the track, and I'll stop it there, and every single one of these trains will now move to the other side of the track and then immediately stop. And then what that is doing is freeing up this line. So I can then pass signals, I can then send, these will then pass, I can then choose a specific set of trains from the RAM to then send all the way back and choose elect to read. And then they pass through the reader, that's the reader there, and then collect here. Then you've got your 128, 164, 32, 16, 8, 4, 2 and 1 are being fed back down here. These will then go all the way, if I follow these down, into here. I mean, this is another reader, which is the switch between 2 different types of reader. But yeah, I then have a system here for loading up trains, and then eventually this will send them into the input to the adder. So yeah, that was kind of the idea. That was the idea here. To basically, so I could come up with a series of programs which would basically configure the adder to choose 2 RAM chips to read from, and select a RAM chip to output to. The thing is that I found that this system, as you can see, used an awful lot of infrastructure. Now I could obviously I could use a lot less than this, but it would become incredibly disorganized. I mean, the biggest problem with this is the fact that there's no copy paste, there's no real quick way to do it. So in order to get this to make sure 100% correctly, it is all built 100% correctly, you have to organize it, and organizing it takes up a lot of space. And also, I mean, it involves an awful lot of trains, because what I have to do is, as well as having all of the trains for here, I then have to have so many different trains for each to control each input and output that it's reading. So, because obviously I can't just have this just for reading them, I also have to have it for writing it, so I have to send commands into the memory to add. I mean, it's really good for quick accessing a memory, because I can instantly just choose a chip and then read it, but I realised that I was going to need a alternative system if I wanted to have a lot of data, and so what I then have been designing is this idea of having a tape system. So this would involve basically trains freely running around this rail, these rails here, and they would go along it. They'd be divided into blocks of 8, but they wouldn't be marked in any way. I mean, they would be counted. So there would then be a counter system here with these here, which would keep track of what point in the tape it was at. It would read. This system would be able to read a byte and then make a decision whether or not to change it. So with that, I could store potentially probably up to 1 kilobyte of data quite comfortably, because I would certainly a kilobit of data, but probably a kilobyte. That would require 8,000 trains, which I'm not sure what the limit on this game is in terms of number of trains it supports. But yeah, I could basically end up having these trains constantly looping around the system. I'd have a reader that would keep track of where it is in the system. So as a train goes round, these then produce counters of where it is. So you could then send to this tape, as I'm calling it, an instruction of what point on the tape you want to read. It would then advance the trains through the system until it got to that part of the tape, read the byte, and then you could also give an instruction of when it's reading to also change the byte. But the result of this is that it would actually be possible to construct a Turing machine purely using trains in OpenTTD, you could have, because you can easily go forwards by just advancing the tape, but in terms of going back one bit, you just have to say I want to go to the previous cycle in the tape, which it would take a long time. It would take an awful lot of time to cycle all the trains through the system until it got to that point, but it would be possible to produce a Turing machine, which would just by diverting trains between tracks, whether it's on the left, whether it's on the top track or the bottom track. And I think that, I don't know that I'll ever get to do that, but I certainly know from doing all of this messing around with this system that it's certainly something that's possible. And I'm no doubt that somebody who's a lot more skilled with using signals in OpenTTD than I am, because I'm very, very much an amateur with this game. I played it when the game originally came out, but the reason that I ended up coming to do this was after a debate with a contemporary friend who is a fan of Minecraft and said to me how amazing it was you could build computers in Minecraft, and I was saying, well, I'm fairly certain you could do, obviously not as advanced as Minecraft, but you could build a functioning computer with older games, and OpenTTD was the leading candidate for me. Although I know that OpenTTD is a modern version of an older game, I think that it does the basic version is fundamentally the same as the original version, although I can't remember exactly if the signals worked exactly the same. Part of the idea behind the design of the computer came from watching Matt Parker's Domino computer on YouTube, and and that basically was like the binary adder was immediately the thing that I thought, oh, I could create that with Trains and Transport Tycoon, no problem. So I recently met Matt Parker after one of his live tours, the Festival of the Spoken Nerd, which I will highly recommend that anybody who has watched this far into this video goes and sees, because. And I showed him the computer and said, look, and obviously, whether he's been polite or not, I don't think he was. I think he was genuinely fascinated by it. One of the questions that he posed to me was, well, what do you think the earliest example of a computer game that you could build a Turing machine was? Now, I knew that a Turing machine had been made in Dwarf Fortress, but I never played Dwarf Fortress. I've seen screenshots of Dwarf Fortress, and I assumed that because of the fact that it's all ASCII art, that it was a really, really old game. But as it turns out, Dwarf Fortress is actually a very new game. Well, I say new, 2006, which certainly makes it newer than Transport Tycoon. And I certainly think that even if you can't build the computer exactly the same way I have, it would be possible to build a computer in the original Transport Tycoon, or certainly the original Transport Tycoon Deluxe. But I would be curious to know if people can think of a game where you could build a functioning Turing machine in the game world using no mods of that game, other than I will allow the fact that I've had to obviously use the cheat codes to give myself an awful lot of money. But that's not changing how the mechanics of the game work. That just means that I've basically given myself the ability to go and fund this infrastructure, which clearly isn't financially viable in the game, because these trains are producing no income, and all they're doing is charging me money for their cost of running and their cost of the cost of maintaining the tracks. But so without making any programming changes to the game, the only thing you'd be allowed to do is to enable a cheat to give yourself unlimited resources. Can anybody think of any games earlier than Transport Tycoon that would be possible to produce something like this? I'm sure there must be some. I would think some in the 80s would be possible, but it would be an interesting question, because as Matt pointed out to me, and I agreed, there will be a point at which games weren't sophisticated enough to do it. Now, one thing I did say in our conversation was, the Game of Life, John Conway's Game of Life, but obviously that's not a computer game. And while there possibly were computer simulations of that much earlier than most famous computer games, I think for the point of the exercise to anybody who wants to try and think of a game which you could build a Turing machine in, it would have to be a game that was specifically a computer game and wasn't designed to be anything but that, but the result of the game mechanics are that you could actually go and say, yeah, this is a Turing machine and this works correctly. So yeah, that's my challenge to people.